Section 2.7 is called Implicit Differentiation, and the first thing I want to kind of talk about is what in the world is the difference between this new section called Implicit Differentiation and what we've done before. So what we have done before is this called Explicit Differentiation. What we've always had is we've had the ability to take a derivative of y in terms of x, where we have y equals on one side of the equation, and we have all of our x's on the other side. That's what we've been doing. In fact, most of the time, almost all the time, it's been given to you as y equals something, or f of x equals something. And on the other side of the equation, all it has is x's. Constants, combinations, quotients, all that stuff, but it's only got x on the right side of the equation. What we're going to do in this section is do implicit differentiation. So either the equation cannot be written as y equals, or, and this sometimes happens too, it's more complicated when we write it as y equals than it would be if we left it as it was. It doesn't say that in that description right there, but I just want you to be aware that there are cases where we could do that. It's just more complicated. The basic idea is that we treat the x and y as variables, and we use all the derivative rules we've learned. Quotients, products, chain rules, but we actually treat y as a variable now instead of sort of as a label on the left-hand side. That's kind of how we treat it normally, right? We kind of treat it y equals as a label. But we're going to actually treat it as a variable in this section, which it actually is. Okay, is everybody pretty well done writing? All right. So we're going to just jump right in and do one so that you can see how this works. We're going to take the derivative, y prime, implicitly. So if you take a look at this particular equation, could we solve this for y? We actually could. There's only one y in there. It's a y squared. But then we'd have to square root the other side, which means we'd end up with a chain rule involved because we'd have a square root involved in it. So this is a pretty simple one that we could actually do if we wanted to move it up the other side. But I'm going to show you how we can use implicit differentiation, and it's actually a little bit cleaner than to actually have that chain rule involved. All right, so here's how this works. What you should notice is that the x squared and the y squared are multiplied together, right? So that means there's going to be a, what rule? A product rule. I've got a product here, right? X squared and y squared are multiplied. That's a product. I'm going to have a product rule. All right, so in the product rule, it says the first thing I do, the way we've done it, is we rewrite the first piece. All good to go? All right, next thing then is I need the derivative of y squared. So what do you suppose is the derivative of y squared, Taylor? 2y. Ah, and your book is going to call it y prime. So you can either put y prime right here or dy dx here. So let me show you what's going on. When we have the y squared, okay, this is just over the side here kind of thing, this derivative is 2y, and then I have to take the derivative of what y is. Well, what is the derivative of y? It's 1 dy dx. So you can either write it as dy dx. That's what the book is that I've used before. Your book is using y prime as the notation. Just as long as you're careful and don't think that's y to the 1 power or something like that, you could use that. The reason is because y is actually a function in terms of x. We just didn't simplify the equation to express it that way, right? Anytime we take the derivative with y, we're going to have a y prime or a dy dx involved in it. Now, you might think, well, then why don't we do that with x? Well, let me show you. The other half of this derivative is to now take the derivative of the x squared. So what's the derivative of x squared? 2x. Now, technically, we could put x prime there. But the derivative of x prime is simply, or the derivative of x is simply 1. We don't have an x prime. There isn't that sort of a notation because x is not a function in terms of something else. We never have the equation solved x equals and so forth. So we don't have an x prime. We don't have a dx dx. In fact, it's kind of nice to think about it that way if you did, because if we did dx dx, what would that be? 1, right? dy dx didn't look like that, did it? It didn't look like dy dy. It's always in terms of x, because that's how we're working with our problem, is in terms of x, because this says right here, y prime of x. X is the inside variable, it's the interior variable. And then I have this times y prime, I'm sorry, y squared, the original function. That's not what it said. There we go. All right. All right, so this is the derivative of the x squared y squared piece. It's a product rule. The other weird thing about the product rule is that in the middle of doing the derivative of y squared, I have the y prime showing up. Okay? The rest of it then actually doesn't have any y's in it. So what's the derivative of the 37? 0. And then I've got the other side of the equation. What's the derivative of the 4x? 4. Okay, that's all the calculus there is right there. You've done all the calculus, just like we've sort of been talking about along the way. The first step is the calculus step. Everything else is algebra, and you're going to get super good at doing algebra, right? You guys are going to all be able to go tutor people in algebra after this class, because you're going to be like, algebra, no biggie. I've done a lot of that this semester. Our goal is to find the derivative of y. I need to actually solve this for y prime equals, okay? So if you notice, there's only one piece that has a y prime in it. It's the first piece right here. So the other piece can be subtracted to the other side of the equation. The piece that I've underlined, I can also rewrite. I'm just going to put the 2 in front. 2x squared y prime. And then this equals 4 minus 2x y squared. What would the last step be? Divide by what, Ben?
2x squared y.
Right, 2x squared y. So y prime equals, and then if you'll notice, we can actually reduce this particular expression on the right-hand side. How? Yeah, there's a 2 involved in all of these coefficients, so I can divide them all by 2. So I actually can write this as 2 minus xy squared over x squared y. Now notice, there weren't any square roots. There weren't any chain rules except for the y squared part of it that had that sort of chain rule involved. That's actually really nice. However, notice the answer right here does have a component of it that's not super friendly. What component of this sort of looks weird based on what we've been doing? There's y's on the right-hand side. Do you guys see that? I have x's. This is y prime in terms of x and y. I have x's and y's on the right-hand side. It's okay. There's nothing wrong with that. It just looks different as part of the solution, right? So this is our final answer. It just looks different than if we'd actually simplified this to y equals to start with and then taken a derivative. Let's try another one. All right, on this one, what do you notice? There's a quotient rule. It's also valuable to notice on this one that y is in more than one location, isn't it? Yeah, this would be really difficult to solve it for y equals. Very difficult. I'm not saying impossible, but it certainly wouldn't have been like the last one. The last one we could have done it. It wouldn't have been too hard. This one would be very complicated to actually make that work. So implicit differentiation on this one is absolutely vital to using this particular function to move forward. So that's a really important feature. All right, so we have a quotient rule, we have a power rule, and inside every time when we take a derivative of y, we are going to have a y prime show up. We're going to have 2 y primes show up because we have y in 2 locations right now. Important to keep that in mind. So the solving for this is going to be a little bit different. All right, so let's get this started. We've actually got a quotient rule like you guys said. So quotient rule, how do I do that first piece, which looks like x plus 3 over y as a quotient? Denominator first, and then what? Close. We do the denominator first. So you're going to have your piece you're talking about is the second piece, actually, Jason. So the first piece is the denominator, and then I need the derivative of the numerator, which is just 1. And then I have minus, and then Jason, you told me y prime, and then what? Times x plus 3. Okay, is everybody good with that numerator? Because y prime is the derivative of y. Down here. The derivative of y is y prime. Is everybody else I mean, are we okay with that numerator? Now's the time to ask if you're not. Okay, denominator then is going to be y squared. All right, we're on the other side of the equation now. What is the derivative of 4x? 4. And what is the derivative of y squared? 2y, and then y prime. All right, the derivative of y squared would be the 2y, and the derivative of the y, which is sort of like an inside function, so there's a chain rule really going on there, is y prime. Okay, there's lots of things we can do. Somebody give me a suggestion.
Multiply both sides by y squared.
That's my favorite plan too. I like that plan. I'd like to get rid of that denominator as quickly or as I can, kind of. So on the left-hand side, this will actually reduce, right? On the right, and then I've got y minus, and I'm going to go ahead and distribute that y prime here because eventually I'm going to need to collect all the y primes anyway. So this would be x y prime plus 3y prime equals.
Would it be not minus 3y?
It would. Thank you. Get that fixed. Good catch. What's on the right-hand side? What do I have? 4i squared plus, good, 2y cubed, and then y prime. Okay, the goal is to solve for y prime, which means everything that has a y prime should all be on the same side, and everything that doesn't should be on the other side. So I think what I'm going to do, because these are negative right now, these y primes here on the right, on the left are negative, is I'm going to move my y primes to the right. It doesn't really matter, but I kind of like to eliminate negatives when I can. And then I'll move that 4y squared to the left. So I'm going to have y minus 4y squared equals 2y cubed y prime plus xy prime plus 3y prime. Okay, is it all showing up there? Does it look okay? All right, so if you notice, what's in common to everything on the right-hand side of that equation? Yep, the y prime, so what can I do? I factor the y prime out. All right, so I have 2y cubed plus x plus 3. Goal is to solve for y prime, so what's the next step? Divide. All right, so the y prime is going to equal that y minus 4y squared that's on the left, divided by the 2y cubed plus x plus 3 that was previously multiplied by the y prime. Sorry, I don't mean to run my line through the 2 there, the squaring, but any questions on that? So the basic idea is if y prime is in more than one location, we're going to collect them all and we're going to factor it out. All right, let's try another one. Same directions, haven't changed at all, but the difference is on this particular one, what do we have? We have trigonometry, and what's the angle? XY, which is a product. So there's a product inside of a chain, right? Because the fact that there's a sign with an angle that's not just x, tells me I've got a chain rule. We did that last time, right? 2.6. And then the fact that the inside itself is a product means I'm going to be using the product rule as well. Okay, so one thing at a time. One thing that might help you to sort of keep this in mind, remember, is that we put these marks around that angle, so that XY, just put that as sort of a circle around there, or well, you could circle if you wanted to, parentheses around the XY. All right, so we're going to start with the outer part, the sine part. What's the derivative of sine? cosine. Everybody knows that one now. And it's the cosine of the same angle, right? Angle doesn't change. This is xy. What happens next is we need the derivative of xy, and that's the product. So the derivative of xy as a product means that I write down the first piece, which means I write down x, and then I need the derivative of y, which is y prime, plus, and then I need the derivative of the x, which is 1, times the original piece of the other one, which is y, exactly. Okay, so as freaked out as y'all looked like deers in the headlights when I said there's a product rule inside, that's not a difficult product rule, right? That one's actually a fairly clean one. That's not too bad. All right, and then on the other side, we've got x squared. So what's the derivative of x squared? 2x. And then minus 3 is nothing. Okay, is everybody good with this so far? Look all right? Okay, so let's actually go ahead and distribute the cosine xy through the product rule piece over here that we got. So I'm going to have x y prime cosine xy plus y cosine xy equals 2x.
So it's not like squared?
What piece is not squared?
Well, it's not like cosine x squared y prime?
Right, that xy prime right there, that xy gets multiplied by the cosine, not by the interior angle. It's kind of like back in trig, I know you guys remember seeing rules where you said things like this, where if you had the cosine of x times 2, this is not the same thing as the cosine of 2x. Right? You can't distribute or you can't combine the multiplication with the angle. So you actually have to write it in the front, and you have different rules that are called double angle formulas or double angle identities and things like that. So same things going on here. Any of the multiplication is occurring multiplying by the cosine, not by the interior angle. Okay, there's only one y prime here, right? So that's actually really nice. What do I need to do in order to solve for that? Okay, so the first thing I can do is I can subtract so that I have 2x minus y cosine of xy. And then I divide by what? So I have y prime equals 2x minus y cosine of xy over x cosine of xy. And there's nothing that can be simplified here. There's not a cosine in all three terms, nor is there an x in all three terms. I'm looking at my denominator. So I can't reduce anything down. This is as simple as it gets. And there's no coefficients like 2's or anything that are in all of the terms either. It's also important maybe to realize that on this particular one back at the beginning, 3, sine of xy equals x squared minus 2, or minus 3, I guess is what it was. There's not a way to solve this very cleanly for y equals, right? You'd have to do some sort of an inverse trig function stuff going on, and right now you don't even know a derivative of an inverse function for trig, so that would be very problematic at this point. So there isn't another way at all to solve this. It isn't just, hey, this would be complicated. It just isn't possible with what you know so far. Okay? All right, let's take a look at a different kind of a question. You'll notice on your homework or on your note sheet, if you've printed it off, it says find an equation of the tangent line at the given point. And then it says if you have a CAS that will graph implicit curves, sketch the curve and the tangent line. And I've drawn a strike through on that part of the directions. It's not even appearing on the screen right now. Most of you don't have that kind of capability. If you do and you wanted to sort of put it into a calculator online, or if you do have a TI-89 or TI-92, you can do that piece. But I am definitely not assuming that you have that capability. So you do not need to do that piece. What I want you to do, what is a CAS? Computer Algebra System. Yeah, so some of the calculators you guys use for the most part, force you to put an equation into your calculators y equals something, right? Some calculators will allow you to put in an equation that looks like this, x cosine y equals 1. And some of the calculators online will allow you to do that as well. But most of the calculators that I have approved for you to use in class, if you will, they don't have that capability. So if you have another calculator and you'd like to do that, that's fine, but you do not have to do that or show that on your homework, okay? All right, so this particular one, the difference in the directions between this and what we've previously had is what? We're finding a tangent line, yes we are. All right, so to find a tangent line, let's see, go there. We need several pieces of information. One of the pieces we need is we need an x and a y value. But look at this. They actually give you that on this particular problem. Now let's just say for a moment they had not given you that. Let's say that they had only given you one of those pieces of information. In fact, the one that would be nice for them to give you would be pi over 3 for y. Could you find the x value?
Yes.
Sure. You just need to know a little trick, right? And if they'd given you the x value of 2, again, could you find the y value of pi thirds? Yes, you could. The direction set that this is going to be included in your book actually gives you the x and the y, so you don't have to do that piece of it. So that's very friendly, right? That's actually more friendly than the problems we've been working. So we have the x and the y, which means the only thing we need is the slope. Very good. And we find the slope by the derivative, you bet. All right, so we're going to take the derivative of this, and it is implicit, right? So notice, what do we have going on here? We have a product rule, very good. What else? Chain rule, because we've got the cosine with y inside of it. All right, so we do the product rule, right? That's the overarching rule, because that's how the two pieces are connected. So the first thing that I need to do is I need to take and rewrite the first piece. X. What's the derivative then of cosine of y? Okay, negative, I'll put the negative in front of the x, sine of y, and then what? All right, times the derivative of the inside, which is y, so that's times y prime. And then we need a plus sign. And then what? 1, because that's the derivative of x. Cosine y, the original of the second piece. And what does all of this equal? 0, because we've got the derivative of the 1 on the right-hand side. We could clean this up a fair bit. We're not going to do too much cleanup. Really, we want to know what in the world does that y prime equal if it's evaluated when x is 2 and y is pi thirds, right? Well, we could just simply put in x is 2 and y is pi thirds, agreed? So that's what we're going to do. We have x is 2, so this is negative 2 at the beginning, sine. Y is pi thirds, so here's pi thirds right in here. Y prime is what I don't know, plus the cosine of y, and the cosine then would be a cosine of pi thirds. How much trig do you remember? Oh, goodness. One of them is square root of 3 over 2, and the other one is 1/2. Which one's which? Yes, it is. Sine is the square root of 3 over 2. And the cosine is 1/2. Okay, is everybody good with that piece? All right, so I could actually move that 1/2 to the other side and make it negative 1/2, agreed? The 2 and the 2 in the denominator, those would reduce. So this is actually just negative square root of 3 on the left-hand side times the y prime. So then what? Right. And I'm actually going to write it as multiplication by the reciprocal. So this would be y prime equals, oh, and they're both negative, so I could also make sure that they change both to positive since I'm going to be dividing by a negative. So this is 1/2 times 1 over square root of 3. And then we could rationalize that. So this y prime ends up being square root of 3 over 6, because the square root of 3 times the square root of 3 is 3 times the 2. There's actually a fair bit of trig in that problem, so any questions on that? We haven't done a ton of uses of trig, but when we do come with them, I want to make sure y'all okay.
So before we rationalized, it was just 1 over 2 square root of 3.
Yeah, it would have been 1 over 2 square roots of 3, and then we'll rationalize that. Any other questions on that? What did I just find? That's my slope. All right, so my equation for my line, I do have more space actually, so I'll just go over here. So I've got my slope, which is square root of 3 over 6. I've got my ordered pair, which is 2 and pi thirds. So I can actually write the equation of my line now. So I've got y minus the y value, which is pi thirds, equals my slope, square root of 3 over 6, times x minus the x value, which is 2. Homework aside, at least when we get to the test, I'm going to have you put this in y equals and simplify it as much as you can. So we're going to distribute that square root of 3 over 6, and we're going to move that pi thirds to the right. So this is y equals, we've got square root of 3 over 6 times x, minus, and then when I multiply that square root of 3 over 6 times 2, what do I get? Right? And we're adding to this pi thirds. You can leave it written that way if you'd like. I actually have the slope times x, and then I've got the ordered pair at the end, that's the b, the y-intercept b at the end. It's a little bit awkward, it looks a little bit funny, so another thing you might see sort of written in the back of the book, or if you want to consolidate it because it does feel a little bit awkward, is you could combine these last two pieces together, since they are, right, y equal mx plus b, they are the b value, and you could write them differently, like you could write them, for instance, as pi minus square root of 3 over 3. They both have a common denominator already, so you can combine the numerators. I just switched the order of the numerators so the subtraction was in the middle. You could put it as negative square root of 3 plus pi if you want, but either of those versions would be fine. Any questions on that? It's all okay? All right. I think we have time for one more, and then we'll stop. So we won't quite get finished with 3.7, or 2.7. Find the location of all horizontal and vertical tangents. This is the first time we've encountered a direction that looks anything like this. So let's actually sort of talk through what the direction's telling us to do, because it does look different. What does it mean if you've got a horizontal tangent line? What's that look like? It's a flat line. What can you tell me about a flat line? Okay, it's constant. What can you tell me about the slope of it? It's the slope of 0. So this is really important, because what do we know? How do we find slope? Well, tangent lines are what we use slope for. We use the derivative to find the slope when we were doing those tangent lines, didn't we? So what we're looking for when we're talking about a horizontal tangent line is we're looking for a tangent line whose slope is 0. So we're looking for a derivative of 0, right? What about vertical tangent lines? I mean, they're straight up and down. The slope is undefined. Well, let's find out what our slope is, and we'll see if we can figure out how to decipher this slope is undefined business. Because it will hopefully come about, and you'll see, oh yeah, that makes sense. Both of these talk about slope, so we need to find the slope, which means we need to find the derivative, right? Now, compared to the ones we've been working on, this one's derivative is not hard. Agreed? It's pretty clean. We don't even have any product rules, do we? All right, so what's the derivative of x squared? What's the derivative of y squared? 2y prime. And Ben, feel free to write dy dx if you want to on your papers. For those of you who've seen that used before in another calculus course, that's perfectly fine. And then I have, what's the derivative of the 3y? 3y prime, very good. Don't forget the y prime on there. And then this equals what? 0. All right, is everybody good to that point? Okay. We need to get this into y prime equals, okay, because we're talking about what in the world can we say about slope. So we need to actually have it solved for what the slope is, which is the derivative. So there's two pieces of this that have y primes. There's one piece that doesn't, so the 2x is going to move, right? And the other two pieces I can factor out the y prime, just like in the last problem, a couple problems up where we actually solved it for y prime. All right, so this is y prime. I've got then 2y minus 3 equals negative 2x. I did a couple of steps there at once. Everybody good? All right. What would be my last step? Mm-hmm. So this is what y prime is.
That's negative 2x, right?
That is negative 2x. Yeah, it doesn't look very clean on top, but yes. Negative 2x on top, and then 2y minus 3 on bottom. All right, so let's talk about the horizontal ones, because those are the ones that you're most familiar with. So to find a horizontal tangent line, I need to figure out where the slope is 0. So looking at this equation, how in the world am I going to get the slope to be 0? The top would have to be 0, right? Because if you do 0 divided by anything, you're going to get 0. The denominator doesn't matter as long as it isn't 0. Agreed? So I need the numerator. So I want to find out where y prime is 0. And in essence, on this particular problem, that's going to be that my numerator equals 0. So my numerator equals 0 when? That's right, when x is equal to 0. This says find the locations, and while I found an x value, what do I also need? A y value. I know that this happens when x is 0, but what in the world, or where in the world is that in terms of the location on my xy plane? I've only got the x value. So how in the world am I going to find the corresponding y value? To where, Mandy?
The original.
The original. I'm going to plug that x equals 0 back into the original equation. All right, so that actually would then look like, in fact, I'll go to my next screen. That would actually look like 0 squared plus y squared minus 3y equals 4. That's the original equation with the 0 plugged in. So now what? What did you say, Ben?
Did you factor out a y?
No, we can't factor out a y.
You subtract them all to one side.
We need it all on one side. When you're dealing with anything that's bigger than a linear power, you have to do factoring. So we don't have any ability to do anything different, but we can do this, and it actually factors pretty clean. So how will this particular one factor? Y minus 4 and y plus 1, which means that the y values are what? 4 and negative 1. So the locations for the tangent lines are actually at x equals 0, y equals 4, and x equals 0, y equals negative 1. There are two locations of horizontal tangent lines, both when x is equal to 0. That does, in fact, at least tell us this is not a function of y in terms of x, because there are two x values with two different y values. How about the horizontal or the vertical tangent line? Let's do that one really quick. Take a look back at that y prime. Y prime is negative 2x over 2y minus 3. What would it look like to have the slope be undefined when the slope is negative 2x over 2y minus 3? Okay, where did you get that from, Ben?
Except what the y part of it is equal to 0 is y part of y.
The denominator, right, Taylor? Yeah, Taylor's saying the denominator. Okay, so if the numerator is equal to 0, we get 0 over something, and that's 0. If the denominator is equal to 0, it's undefined, right? So the vertical tangent line is equivalent to where the denominator is equal to 0. So for my vertical tangent line, it's equivalent to having my denominator equal to 0. And the denominator was 2y minus 3, and this actually solves for y being equal to 3 halves. Right? Add the 3, divide by 2. Again, that's only the y value, so what do I have to do?
You don't get the original.
Put it back in the original and solve for x, yeah. So I've got x squared plus 3 halves squared minus 3 times 3 halves equals 4. All right, so what's 3 halves squared? 9 fourths. I've got 3 times 3 halves, which would be 9 halves, equals 4. What is 9 fourths plus 9 halves?
27 fourths.
That sounds right. 27 over 4. You guys okay with that?
Right, first minus.
Oh, it was minus. That is correct. I totally misspoke. We have 9 fourths minus 9 halves, so this 9 halves would actually be 18 over 4. So we have, that would be negative 9 halves. Yes. I'll fix it. Thank you. And then we can add the 9 fourths to the other side, right? So this is x squared equals, let's see, how about we write that 4 as 16 over 4 plus 9 over 4, which is 25 over 4. So what's my x value going to be?
5 over 2,
Close.
plus or minus.
All right, so we have a x squared, so we take a square root. And when we take the square root, we get a plus or a minus of the 5 halves. So there are 2 vertical tangent, how did we say it? What was the directions? 2 vertical tangent lines, 2 locations of vertical tangent lines. One is at x equals 5 halves, y equals 3 halves. The other one is x equals negative 5 halves, y is equal to 3 halves. Two vertical tangent locations and 2 horizontal tangent locations. Any questions on that? All right.